Swayam Prabha. Digital India. Educated India.
Hello student, in this class we will discuss about linear problem. So, let me explain what is linear problem. So, in the last class we have discussed about optimization problem. So, what is the necessary condition for optimality, what is the sufficient condition for optimality both for a single variable problem as well as multivariable problem. Okay. So, today we will discuss linear problem. So, let me explain what is linear problem. Now, an optimization problem can be represented as a minimization problem, and there may be some constraints, like we may have inequality constraint that zx is less than equal to 0. So, we have total j number of constraints, and these constraints are inequality constraints. So, in this case this is less than equality type constraint. So, you may have greater than equality type constraints. Suppose sometime you may have this type of constraint. So, in this case I can convert this problem to a less than equality type constraint by multiplying -1. So, if you have greater than equality type constraint, so I can convert it to less than equality type constraint by multiplying -1, or other way also I can do. If you have less than equality type constraint, so you can convert it to greater than equality type constraint. Okay. So, let us discuss this problem. So, we may have inequality constraint that zjx less than equality type, or we may have equality constraint like hkx equal to 0, and suppose we have total k constraint. So, altogether we can say that this is an optimization model. So, what we have in an optimization model, one is objective function. Objective function can be a minimization type, but we may have maximization type objective function, suppose maximization of f x. So, in that case I can also convert a maximization problem to a minimization problem by multiplying -1. So, a maximization of f x is equal to minimization of minus of f x. So, I can convert that problem like a minimization problem, or I can also convert a minimization problem to a maximization problem. Okay. So, altogether a problem will have an objective function. So, this is objective function, and we will have constraint. So, we will have constraint. This constraint may be inequality type constraint like zjx less than equal to 0, or we may have equality constraint hkx equal to 0. Now, if f of x, zx and hx are linear, so all of them are linear function. So, in that case the problem will be called a linear problem. Okay. So, I hope this is clear. If the objective function, that is f x, the constraint, that is zx and hx are linear. So, in that case we will say that the problem is a linear problem, otherwise the problem is a non-linear problem. So, we will discuss both linear and non-linear problems, but in this particular class today we will discuss about linear problem. Now, what is linear programming? So, linear programming is an optimization method. Okay. So, this is an optimization method applicable for the solution of optimization problem where the objective function and the constraints are linear. So, what is linear programming? So, it is an optimization method. So, it is an optimization method applicable for solution of an optimization problem where objective function and the constraints are linear. Okay. So, as I said, the both objective function and the constraints should be linear. So, in that case the problem is known as linear problem, but the solution procedure or solution or you can say the optimization method is called linear programming. It was first applied in 1930 by economists mainly for solving resource allocation problem. Suppose you have limited resources and you want to allocate optimally. So, in that case this optimization linear problem or linear programming method can be applied, and people have used basically for resource allocation. Okay. So, it was as I said, so it was first applied in 1930 mainly for solving resource allocation problem. During World War II this linear programming was used. So, during World War II the US Air Force sought more effective procedure for allocation of resources, and they have used linear your programming, okay, for allocation of resource. Then George B. Danzis, a member of US Air Force, formulated general linear problem for solving the resource allocation problem. Okay. So, he was a member of US Air Force and he actually devised a method for allocation of resources, and it is a linear programming method, and the device method is known as simplex method. So, we will also discuss about this method in this class. So, we will discuss. So, it was given by George B. Danzis. Now, it is considered as a revolutionary development that help in obtaining optimal decision in complex situation. The linear programming is considered as a revolutionary development that helps in obtaining optimal decision in complex situation. Some of the great contributions are, as I said, that George B. Danzis. So, he devised simplex method. So, we will discuss actually. So, this is a method for solving a linear problem. So, we will discuss that one. Then Kuhn and Tucker, they have given duality theory in LP. Then Sarnes and Cooper, they have worked on industrial application of LP. Then Karmarkar, so he has given Karmarkar's method. So, this is also a method for solving a linear problem, and Nobel Prize was also awarded for contributions related to LP. Nobel Prize in Economics was awarded in 1975 jointly to L.V. Kantorovich of the former Soviet Union and T.C. Koopmans of USA on the application of LP to economic problem of resource allocation. Okay. So, Nobel Prize was awarded for their work and their work was basically applied to resource allocation, and they got Nobel Prize in 1975. So, this is some of the history related to linear programming. So, let us go to the linear problem. Now, standard form of linear problem. A linear problem, as I said, that I can define as a minimization problem. So, here minimization of f x. So, now I may have n variable x 1, x 2, x 3, x n variable. So, this is a linear function. So, therefore, the function could be c 1 x 1 plus c 2 x 2 plus c 3 x 3 plus c n x n. So, this is your objective function and subject to the linear constraints. Okay. So, this is the standard form. So, in the standard form this must be equality sign. Okay. So, this must be equality, it cannot be less than equality type or it cannot be greater than equality type in case of standard form of linear problem. So, we may have total m constraints. So, in this case m number of constraints. So, this is number 1 constraint, this is 2, this is 3, like this is your m constraint. So, we have m constraint, and how many variable we have? So, we have total n variable. Okay. So, n is the variable, number of variable, okay, and m that number of constraints. Okay. So, in this case, so this is a standard form, as I said. So, it is a minimization type problem, but you need not worry if your problem is a maximization type. So, you can convert your maximization problem to a minimization problem, and the constraints should be equality type constraints. So, it must be equality type constraint, but if you have inequality type constraint, so you have to convert your problem to a equality type constraint. So, that also we will discuss. So, in the matrix form, so I can write the standard form of linear problem like this. So, it is a minimization of f x. So, this is C transpose x and subject to a x equal to b, and the all variable x is should be greater than equal to 0. Okay. So, this is in matrix form. So, this is the objective function, and this is your objective function, and these are your constraint, and this constraint should be of equality type constraint, and the all variable, all decision variable should be positive. That means, it should be greater or equal to 0. So, where x is a vector, so x equal to x 1, x 2, x n, then b is the right hand side, that is b 1, b 2, b n. C is equal to C is also a vector. So, that is C 1, C 2 up to C n, and A is a matrix. So, this matrix can be written A 1 1, A 1 2, A 1 n, then A 2 1, A 2 2, A 2 n, and we have total m constraint. So, therefore, A m 1, A m 2, A m n. So, this matrix this is a matrix. Okay. So, I can write a linear problem in this matrix form, or otherwise also I can write in algebraic form. Now, the standard format is saying that the objective function is a minimization type. Okay. So, it is a minimization type. All constraints are equality type, that means, all constraints should be of equality type. Okay. And all the decision variables are non-negative. So, these are the three conditions of a standard form. So, if your problem satisfied these three conditions, then I will say that the linear problem is in standard form. Okay. Now, question is that you may have that your objective function is a maximization type function. Then what you have to do? You have to convert, in order to convert to the standard form, you have to convert the maximization problem to a minimization problem. Similarly, if your constraints are not equality type constraint, then what you have to do? You have to convert it to equality type. And similarly, if all the decision variables are not positive, okay, it is not non-negative. So, you have to have some method, so that all decision variables are positive. Okay. So, now let us discuss, if your problem is not in a standard form, then how can you convert your problem to standard form? So, the first condition is the objective function should be of minimization type. Okay. Now, what you will do? So, for maximization problem, suppose your problem is a maximization type problem, that is maximize C 1 x 1, C 2 x 2, C 3 x 3, C n x n. So, what you have to do? You have to convert your objective function to a minimization type function. So, to do that, what I will do? I will multiply it by -1, okay, and then your objective function will be converted to a minimization type problem. So, now if you multiply it by -1, then what you will get? Minus C 1 x 1 minus C 2 x 2 minus C 3 x 3 minus C n x n. So, therefore, to convert your problem to a standard form, if your objective function is a maximization type function, just you multiply it by -1 and that will convert your problem to a minimization type problem. The next condition is the all constraints are equality type. Okay. So, that means a k 1. So, this is a particular kth constraint a k 1 x 1, a k 2 x 2, a k 3 x 3, a k and x n which is equal to b k. But if it is less than equality type constraint, that your constraint is not equality type constraint, but it is a less than equality type constraint. So, what you have to do in order to convert it to standard form? So, you have to make this equality sign. So, how you will do that? So, it can be converted by adding a variable here, there is a extra variable I am adding here, and this extra variable so is n plus 1. So, we have total n variable up to x n. So, I am adding another variable in order to make it equal. Okay. So, equality sign. Now, you see this constraint is a equality type constraint. So, earlier it is a less than equality type constraint. So, by adding x n plus 1, by adding an extra variable here, so we can convert this particular constraint to equality type constraints. Okay. Similarly, if you have greater than equality type constraint, okay, so this is the sign. Now, it is not less than equality type, but it is a greater than equality type constraint. So, what I can do basically, so I can subtract another variable that is x n plus 1, and in order to convert this particular constraint to a equality type constraint. So, what I will do basically, if it is less than equality type, then I will add a variable, and if it is greater than equality type, then I will subtract a variable to make it equality type constraint. Okay. So, this variable is known as when you are adding. So, when you are adding a variable, this variable is known as slack variable, and when you are subtracting a variable, then this variable is known as surplus variable. So, if it is a less than equality type, you are adding a variable and name of the variable is slack variable, and if it is greater than equality type constraint, so you are subtracting a variable. So, in that case we will call that variable as a surplus variable. Okay. So, by using a surplus variable or a slack variable, so I can convert a non equality type constraint to equality type constraint. Now, the third condition, that all the variable should be non-negative, that means should be positive. Okay. So, but you may have some negative variable. Okay. So, in some cases you may have negative variable. So, it means that x 1, x 2 up to x n should be your positive, but when you have a negative variable, suppose x j is unrestricted in sign, that means x j can be negative also or it can be positive also. There may be some problem sometime that a particular variable can go or can have a negative values. Okay. So, in this case suppose x j is unrestricted in sign, that means the variable can have a negative value. In that case what I will do, I can write x j equal to x j dash minus x double j dash. So, by doing that, where x j dash and x j double dash, so that is actually positive. Okay. So, that is these two are positive, but x j can be negative also depending upon what are the value of x j dash and x j double dash. Suppose I would like to have a negative value of x j. So, what I can do, this is suppose 4 minus 5. So, x j will be equal to minus 1. Okay. So, I can have a negative value something like that, but in LP problem. So, what I will have in place of x j, I will have two variables and both the variables x j dash and x j double dash should be positive. Okay. So, should be positive. So, in that case, so if you have a variable which is unrestricted in sign, so I can convert that particular variable or I can write that variable like this, and I can have actually two other variable which are positive, and but results will be negative, xj will be negative. Okay. So, by using these three rules, okay, we can convert a linear problem to its standard form. So, we can convert the linear problem if it is not in standard form. So, we can convert it to standard form. So, let us take a set of linear equations. Okay. So, suppose there are m equations and n decision variables. Okay. So, we have total n decision variables and total m equation. Now, see the conditions. The first condition is that m is greater than n. So, what does it mean? There are m minus n redundant equations which can be eliminated. Okay. So, in this case what is happening? The number of equations is more than the number of decision variables. So, in that case we will have m minus n redundant equations and which can be eliminated. So, this is the first condition. Now, second condition is that if m equal to n, that means the number of equation is equal to the number of variables. Okay. So, there will be an unique solution in this case and there may not be any solution. Okay. So, we may have an unique solution in this case if number of equation is equal to number of variables. So, in that case we may have a unique solution or there may not be any solution. Okay. So, this is the second condition, and the third condition is that if number of equation is less than the number of variable, number of equation in this case is less than number of variable. So, this is a case of undetermined set of linear equations. If they have any solution, there may be innumerable solutions. Okay. So, in this case if there is a solution or if they have any solution, in that case there will be innumerable solution if the number of equations is less than the number of variables. So, in that case if there is any solution, there will be or there may be innumerable solutions. So, the problem of linear programming is to find out the best solution that satisfy all the constraints. Okay. So, the linear programming, so that we are discussing here. So, if this is the case, if this is the third case, basically I am talking about the third case when the number of equations is less than the number of variable. So, in that case if there is a solution, as I said, so we may have innumerable solution. Then the problem of linear programming is to find out the best solution, because you have more than one solution, you have multiple solution in this case, and the problem of linear programming is to find out the best solution that satisfy all the constraint. Okay. So, that is the function of linear programming. So, what we want to do? So, we have multiple solution, we may have innumerable solution, and out of this solution we would like to find out the best solution, and that is the function of the linear programming, or you can say the objective of linear programming. So, we would like to find out the best solution. Now, let us see this linear problem. So, here this is a maximization type objective function, maximize z equal to c1 x plus c2 y. So, I have taken a two variable problem in order to draw it. Okay. And this is a maximization type problem, as I said, z equal to c1 x plus c2 y subject to a1 x plus b1 y less than d1, and similarly a2 x plus b2 y less than d2, and x and y, this should be positive. Okay. This should be positive. So, let us plot it. So, this is y equal to 0 and this line is x equal to 0, and this part is infeasible region. Okay, because the x and y should be positive. So, if it is in this side, the x value will be negative, and in this side y value will be negative. So, therefore, this is infeasible region. Okay. So, this is x equal to 0 and this is y equal to 0. Now, if I plot the constraints, so the first constraint is a1 x plus b1 y equal to d1. So, this is the constraint and this is a less than equality type constraint. So, therefore, this region is infeasible region. Okay. Then second one is a2 x plus b2 y equal to d2 and this is also less than equality type. So, this is the line a1 x plus b1 y equal to d1 and this is the region which is a1 x plus b1 y greater than d1 and this is the side and these are the side where it is less than d1. And similarly, this is the line which is a2 x plus b2 y equal to d2 and this is your infeasible region, and this part is feasible region. Okay. So, this is feasible region. So, now if I say that if I take any value of z, okay. So, suppose z equal to p1 and then if I draw this particular line, so I am getting z equal to p1. Now, if I increase the z value, that means this is the increasing direction, then maybe this may be one line and I may get this solution. So, this is one solution you may get or there may be other solution also. Now, because our objective is to maximize the value of z, so in this direction z value is increasing and finally, I am getting a solution here. So, this is the solution which is the best solution, because after that if I draw any line then this will be in infeasible region. So, whatever solution you are getting, it will be in infeasible region. So, therefore, this is a particular solution which is basically the maximum point, you can say this will maximize this particular function, I will get the best solution somewhere here. Then similarly, if my z is something like that, so this is the z equal to p1, this is the increasing direction in this case, this is the increasing direction. I may have one solution here, I may have one solution here. So, maybe this is basically this may be the best solution in this case, and if I increase this value, so then it will be on the infeasible region. So, therefore, this is one of the solution of this particular problem and probably the best solution. So, as such, the solution of the problem will be one of the corners of the search space. So, what we are getting here? So, one of the solution will be either here or here or here, depending upon the objective function. Okay. So, solution will be one of the corners. Now, suppose if your z function is like this, then what will happen? So, finally, this is the maximum value of z I am getting. So, this is the maximum value of z I am getting. So, in this case, this is also one solution, this is also one solution, and there are several solutions in between. So, in this case, this problem has infinite number of solutions. So, I will have infinite number of solution, that means any solution on this particular line, feasible solution on this particular line is the maximum solution. So, in that case you can say that this particular problem has infinite number of solution. Let us see this problem. So, here this is the infeasible site. So, this is the infeasible site and this is the infeasible site. Okay. And in this case, so this entire search space is basically the feasible search space. Okay. So, this is the feasible region. This is also infeasible part because x and y should be positive. So, anyway, so this is also infeasible, something like that. So, now in this case this is the feasible region. Now, if I take any z, then basically we can continue. Okay. So, there is no limit, I can go up to infinity in this case. So, therefore, this particular problem is unbounded problem, and this problem, this is the problem of unbounded solution. That means, the solution will be infinity. So, you can go along that direction and there is no bounding. So, we can say that this particular problem is an unbounded problem. Now, let us discuss search space. Okay. So, I will explain what is convex search space and what is non-convex search space. So, this is a convex search space and this is also a convex search space. Now, if I see that this search space is not convex, similarly this is also not convex. Let me explain why these two are non-convex search space and this is convex search space. Okay. So, for this particular search space, if I take any 2 point, suppose if I take any 2 point and if I draw a line, then whatever points on this line will be within that search space. So, you take any 2 point within, maybe I can take these 2 point and all the points are within the search space. Similarly, if I take any 2 point, then all the points or this line is within that search space. Now, question is, in this case, if I take these 2 points, then if I draw this line is within this search space, but I can also take these 2 points. When I draw, this line is not within the search space. So, therefore, this is a non-convex search space. Similarly, if I take these 2 points, this particular line is not within the search space and this search space is a non-convex search space. Okay. And anyway, so this is not a linear search space, but this is a linear search space and this is also a convex search space, because I can take any 2 points and if I draw, this particular line will be within that search space. Similarly, in this case also, this, if you take any 2 points and if you join these 2 points, and that particular line will be within that search space, but this is also a non-convex search space, because the line will be not within the search space. Similarly, here also this is a non-convex search space. So, I will discuss the mathematical definition of what is convex search space and what is non-convex search space later on. So, as I have explained, you take any 2 points and you draw a line, and if the line is within that search space, so in that case the search space is called a convex search space. And but if suppose if you take any 2 points and you join that 2 points and you whatever line you are getting, if that line is out of that search space, so in that case the search space is a non-convex search space. So, I will discuss it and I will give you the mathematical definition of convex search space. Now, if you look at all this search space, then this is a linear search space, this is also a linear, this is also linear, and this is a non-linear search space. This is linear, this is non-linear, this is non-linear, and this is non-linear. So, when we are talking about linear problem, so your search space, so whatever the equation, okay, so these equations will be a linear equation. So, your search space may be like this, may be like this, may be like this. Okay. Now, as I have said or I have explained you already that the solution will be, so whatever optimal solution will be in one of the corners. Okay. So, either in this corner or in this corner or in this corner or in this corner or in this corner. Okay. So, therefore, whatever method you want to develop or you want to use, basically that I would like to see the corners of the search space, because solution will be either in one of these corners. Okay. So, the method should be developed in such a way that you are not actually looking at any solution on the other part except these corners. Okay. So, this is you can say one property of linear problem, that your solution will be in one of the corners of the convex search space. Now, let us have some definitions used in linear problem. So, first one is the point of n dimensional space. Okay. A point x in an n dimensional space is characterized by an ordered set of n values or coordinates. Okay. The coordinates of x are also called the component of x. So, what a point of n dimensional space? A point x in an n dimensional space is characterized by an ordered set of n values, or I can say that n coordinates. The coordinates of x are also called the component of x. Okay. So, line segment in an n dimensions, if coordinates of 2 points x 1 and x 2 are given, the line segment L joining these 2 points is the collection of points x lambda whose coordinates are given by this equation. So, x lambda is lambda x 1 plus 1 minus lambda x 2. So, lambda is between 0 and 1. So, if you are putting 0, if I put 0, lambda equal to 0. So, I will get this particular point x 2, and if I put lambda equal to 1, I will get this particular point, and if I take lambda equal to 0.5, so I should get the midpoint. Okay. So, I should get the midpoint. So, therefore, by varying the value of lambda, so I can get any points on this particular line. Okay. So, line segment in n dimensions. So, if coordinates of 2 points x 1 and x 2 are given, the line segment L joining these 2 points is the collection of points x lambda whose coordinates are given by this particular equation. Okay. So, I hope this is clear to you. Now, what is hyperplane? In n dimensional space, the set of points whose coordinate satisfy a linear equation a 1 x 1 plus a 2 x 2 plus a 3 x 3 plus a n x n equal to a transpose x equal to b, or I can write this is a transpose x equal to b. If these points satisfy this particular equation, and then we will call it as a hyperplane. Okay. A hyperplane is represented by HAB. Okay. So, it is represented by HAB, which is A transpose x equal to b. A hyperplane has n minus 1 dimension, where n is the number of variable. Okay. So, a hyperplane has n minus 1 dimension in an n dimensional space. Okay. So, that means it is a plane in 3 dimensional space, and it is a line in 2 dimensional space. Okay. So, this is your hyperplane. Now, I have shown a hyperplane in 3 dimensional space. So, this is a plane, as I said, and I can say that this is H positive and this is H negative. So, H positive is that A transpose x greater than B, and H negative is A transpose x less than your B, and this is in case of line. So, this is H negative and this is H positive. Okay. Now, what is convex set? So, I have already defined what is convex surface, and let us see what is convex set. A convex set is a collection of points such that if x 1 and x 2 are any 2 points in the collection, the line segment joining them is also in the collection. Okay. So, which can be defined as that if x 1 and x 2 is in the collection of S, then x is also in S. So, where x lambda, that means I am joining these 2 points, that is lambda x 1 plus 1 minus lambda x 2 are also in that particular collection. So, where this is basically lambda is between 0 and 1. So, what I am saying that if any two points, suppose I am telling about the convex search space. So, this is basically a convex search space, and if you take any 2 point, this is x 1 and this is x 2, and suppose this is x 1 and this is x 2, and you are joining these two lines, and this line I can represent by this particular equation. So, whatever value of this x lambda, it should be within that your collection. Okay. So, in that case I will call that this set is a convex set. Now, vertex or extreme point. So, these are the vertex or extreme point of the search space. Now, what is feasible solution? In a linear programming problem, any solution that satisfy the conditions, that condition means the constraints. Okay. So, a x equal to b and x greater than 0, so is called feasible solution. So, what is feasible solution? In a linear programming problem, any solution that satisfy the constraints and non-negativity, this is also a constraint, is called feasible solution. So, I will say a particular solution, if that particular solution is satisfying the constraints including the non-negativity constraint. So, in that case that solution is a feasible solution. Okay. Now, what is basic solution? Now, a basic solution is one in which n minus m. Okay. So, here n is the number of variables and m is the number of equation. So, what we are doing? A basic solution is one in which n minus m variables are set equal to 0 and solution can be obtained for m number of variables. Okay. So, what you will do? Suppose n is the number of variables and m number of equations. Okay. Now, in this case what is happening, that n is greater than m, that means the number of variables is more than number of equation, that third condition or we have discussed already. So, let us take this example problem. Suppose there are 3 equations, here and number of variables is 4, that means 4 variable, that is x 1, x 2, x 3 and x 4, and we have 3 equations. So, what I will do, that n minus m. So, in this case that 4 minus 3 equal to 1. So, one variable is set equal to 0 and we will try to find out the solution of the problem. Suppose one variable, you may take any variable. Suppose if I say that x 4 equal to 0. Okay. So, x 4 equal to 0. So, then now I have x 1, x 2 and x 3. So, I can find out what is the value of x 1, x 2, x 3. Okay. So, that I can find out, and x 4 is equal to 0. So, in that case I will say that this solution, whatever solution I am getting, that this solution is a basic solution. I hope this is clear. So, in this case what we are doing, that n minus m variables are set equal to 0 in this case. So, in this particular case we have 4 variables and 3 equation, therefore, one variable will set equal to 0. So, one variable means any variable, suppose I have taken x 4, but you can also take x 2. Okay. So, in that case whatever solution you are getting, this solution we can say it is a basic solution. Now, what is basis? The collection of variables not set equal to 0, to obtain the basic solution is called the basis. okay, the collection of variable not set equal to 0. So, I can say that the example problem we have taken, suppose x 4 we are putting 0, x 4 we are putting 0 and x 1, x 2, x 3 are not 0. So, what the definition? The collection of variable not set equal to 0. So, in this example problem, what are the variable? This is x 1, x 2 and x 3, they are not set to equal to 0. So, they are not 0. So, I am not putting them considering them as 0. So, this collection is known as the basis. Okay. So, here x 1, x 2 and x 3 are in basis. Okay. I hope this is clear. Now, next is, so we may also take like that, suppose if I say that I would like to make x 1 equal to 0. So, if I say that x 1 equal to 0, x 1 equal to 0. So, in that case x 2, x 3, x 4 we are not setting equal to 0. So, they are not 0. So, therefore, x 2, x 3 and x 4 will be on the basis. Okay. So, the collection of variable not set equal to 0. So, in this case x 2, x 3 and x 4, in earlier case it was x 1, x 2 and x 3. So, they are in basis, or we can say this is the basic variables. Now, next is what is basic feasible solution. So, this is the basic solution. Basic solution, already you know what is basic solution. So, this is the basic solution that satisfies the non-negativity conditions. Okay. So, non-negativity conditions, that is your basic feasible solution. So, feasible solution also should satisfy the non-negativity conditions. So, then we will call basic feasible solution. Next is non-degenerate basic feasible solution. So, this is a basic feasible solution that has got exactly m positive x I. So, in that case we will call it non-degenerate basic feasible solution. We will discuss this when we will solve the problems. And finally, what is optimal solution? A feasible solution that optimize the objective function is called an optimal solution. Okay. So, the feasible solution, a feasible solution, because as I said, so when n number of variables is greater than number of equation, so in that case we may have innumerable solution. Then a feasible solution that optimize the objective function is called the optimal solution. Okay. So, that will be the optimal solution, and basically our objective is to find out the optimal solution of this problem, and that solution must be a feasible solution. Now, let us take a system of linear simultaneous equation. Okay. So, suppose I have this equation, that is a11 x 1 plus a12 x 2 plus a13 x 3 plus a1 and x n equal to b1, and I have named it as E1. And similarly, I have another equation, that is E2, that is E3, and total equation is n equation. So, in this particular problem we have n variable and n number of equation, that is number of variable is n and number of equation is also n. Okay. So, what we can do basically, so I would like to solve, I would like to find out the value of x 1, x 2, x 3. Okay. So, I would like to solve these linear equations. Okay. So, what I can do, I can apply the elementary operation. I think all of you know that, we have already did it. So, what I can do, any equation E r, so any equation suppose E r can be replaced by k E r. Okay. So, I can multiply equation by a constant. So, that I can do, and where k is non-zero constant. Okay. So, the equation will not change if I multiply a particular equation by a constant. Similarly, what I can do, any equation E r can be replaced by E r plus k E s, where E s is any other equation. In that case also the solution will not change. Okay. And this too is known as elementary operation. I can do that. So, first one is that I can multiply a equation by a constant, then solution will not change. Okay. So, this is one, and second one is I can replace a equation E r by E r plus k E s. Okay. So, then also solution will not change. So, by using these two operations I can solve this problem. So, let us see using this elementary row operation, we call a particular variable can be eliminated from all but one equation. This operation is known as pivot operation. So, what I can do? I can eliminate a particular variable from all the equation but one. So, in one equation I will keep, and I would like to eliminate that variable from the other equation, and using these two operations, whatever row operation we have discussed, and this operation is known as pivot operation. So, idea is that, so in this particular case, so what I am doing, that I am eliminating this x 1 variable from the other equation. Okay. So, you just see here it is 0, here it is 0, here it is 0. My objective is to eliminate this x 1 variable from the other equation. So, I am keeping only on the first equation, and I am eliminating from the other equation. Similarly, the x 2 variable I am keeping in the second equation, and I am eliminating from the other equation. Similarly, x 3 variable I am keeping at the third equation and eliminating from the other equation, and finally, I am keeping x n variable in the last equation and eliminating from the other equation. So, as I said that it is not that you have to keep the variable x 1 in the first equation, it is not like that. So, the variable x 1 has to be kept at the first equation. So, you can also keep in the second equation, you can take any order, but here I have shown you that you are keeping the variable 1 at the first equation, variable 2 in the second equation, 3 in the third equation, and nth variable in the nth equation. So, in this order I have said, but it can be in a different order also. So, now if I can transform this set of linear equation, if I can transform in this form, then what is the solution? You just see that in the first equation we have only one variable, that is x 1, x 2, the coefficient of x 2 is 0, x 3 is 0, x n is 0. So, therefore, from the first equation I will get that x 1 equal to b 1 dash. Similarly, from the second equation I will get, you just see the variable of x 1, x 3 up to x n is 0, only we have x 2 variable. So, x 2 will be b 2 dash. Similarly, from this I can find out x 3 equal to b 3 dash, and from the last equation I can find out that x n equal to b n dash. So, what is the solution? Solution is x I equal to b I dash for I equal to 1, 2, 3 up to n. Okay. So, using this row operation, so I can eliminate a particular variable from all the equation, but keeping at only one equation, and if we can transform our equation like that, the way we are doing here, I can easily find out the value of x 1, what is the value of x 1, x 2, x 3 and x n. So, I can do that. I think this operation, as I said, so this operation is known as pivot operation. Pivot operation means I am keeping a variable in one equation, and for other equation the coefficient of that particular variable is equal to 0. Now, if the number of variable is more than number of equation. Okay. In the earlier problem, the number of variable is equal to number of equations, but in this case the number of variables is more than number of equations. So, we have now n variable and we have m equation. So, what I can do? So, in this case the n is greater than m. So, here what we are doing? We are applying the row operations, and up to the number of variable m we are doing the pivoting. That means, what we are doing here, for the x 1 variable the coefficient is 1 and for others coefficient are 0. Similarly, for x 2 only in the second equation this is 1 and other equation that is 0 up to x m. So, x m the coefficient is 1 and for others the coefficient are 0. Okay. And we can say that this is the basic variable and these are the non-basic variable. So, for non-basic variable, that is from m plus 1 to n. Okay. So, m plus 1 to m we call it non-basic variable, and what we will do for the non-basic variable, we will set equal to or this variable will set equal to 0. Okay. So, one possible solution. So, these are pivotal variable and these are non-pivotal variable and these are the constants. Okay. So, therefore, for this particular problem one solution. So, one solution can be determined from the system of equation is that x I equal to b I dash. Suppose if I say that this particular variable is equal to 0, this particular variable is equal to 0. So, therefore, I can say that x 1 equal to b 1 dash. Similarly, if I say that this is 0 and this is 0. So, x 2 equal to b 2 dash, and similarly if I say that this is 0 then x 3 equal to b 3 dash. Okay. So, one solution is that x I equal to b I for I equal to 1 to m and x I equal to 0 for I equal to m plus 1 up to n. Okay. So, that means for the basic variable I am finding the x I equal to b I, and for the non-basic variable. Okay. So, for the non-basic variable x I equal to 0. So, this is one possible solution. So, this solution is called basic solution. So, what is basic solution? Already we have discussed that this solution is called basic solution. That means, for the non-basic variable we are setting it equal to 0 and for the basic variable that x I equal to b I. Okay, then let us stop here. So, we will continue our discussion in the next class. Thank you.